Bluetooth channel sounding has created quite a lot of buzz recently as a new distance measurement technology, but there's always been a bit of a question as to how well it will work in practice. Well, we now have some products so we can actually look at this. So in this video, we're going to test how well it works as a distance measurement technology and compare it side by side with ultra wideband, another technology. Now, just to make Insight SIP's position clear on this, we have products in both technologies, so we don't really, we're not favoritizing, making one of these a favorite. We're happy to provide either. So what we want to do is to show objectively, as far as possible, the strengths and weaknesses of each technology. So first we'll have a look at the products that we're using in this comparison. So the first one is the ISP2454LX. This is a new product based on the Nordic NRF54L15 product. So it's brand new and it has the latest channel sounding technology built in. It's a great product. It offers a big upgrade compared with previous generations of Bluetooth devices. It's just better in pretty much every respect. Faster processor, more memory, better power consumption. You name it. It's got a lot of advantage. But the particular aspect we're looking at here is the distance measurement channel sounding technology. So for the UWB side, we're using the ISP3080, which is a product that's a little bit more mature, but it still represents latest generation technology. And so in this one, the UWB is provided by a chip from Qorvo, the Qorvo QM33110. It's a dual radio UWB BLE device, but the BLE it's not one that supports channel sounding. The BLE is there for other reasons. So it's the UWB radio that we'll be testing out in this video. So let's have a quick look now at the boards that we're using to do these tests. So at the top we have the channel sounding. So at one end we just simply have one of our standard test boards with a module mounted on it. And the other end, we have the test board mounted onto our interface board, which is what you get in the evaluation kit, and then that's plugged into the PC. Now, it's important to note here that for this and for the UWB, you don't need it to actually do the measurement. You only need the module with some power attached to it. You do not need anything else. You can do the measurement between two modules powered up and nothing else is required. So the only reason we have these other connections like to the PC, as we do in both the UWB and the channel sounding, is just so we can read out the data and display it for you. But the actual measurement could be done just with a module, and then that module could send its results somewhere else via BLE, for example, so that you could do distance measurement quite happily with just a module powered up by a battery. So then for the UWB, which is the lower one, again we have a little tag board with a module and a battery and not much else really. And then we have an anchor board, which is basically the module. Here we've connected an external antenna just to give a little bit more range. But again, it could just be a module on its own and you would be able to do the measurement perfectly well. And then again, you connect that to the PC, which in this case is just so we can get the data out and display it. So this is the boards mounted outside in the car park outside our offices. So here you have the initiator, which is the channel sounding board that will be connected to the PC. So yeah, you see that it's just mounted on a pole there, and then at the other end with a tape measure between the two to measure the distance, you've got the reflector, which is just the test board, which is this one. Now with the UWB, I'm not going to show you all that again, but essentially it's using exactly the same setup and poles, just with the UWB boards in place of the ultra wideband ones. And then for the inside measurements, we've just chosen a random bit of our office to record in. So this is what you would expect to be a more challenging environment. There's walls, there's partitions, there's metal desks. So lots of things that you could get reflections from. So again, we have the initiator here plugged into the PC, and then tape measure stretched out, and the reflector at the other end, which is just the test board for the channel sounding side part, stretched out across the floor, and which we move around to take the measurements. And then for the UWB, we just repeat exactly the same thing, swapping the boards for UWB boards, but with exactly the same setup. So we can do a like-for-like comparison in this office environment that is, represents an indoor environment, shall we say. It's reasonably typical, I guess. I mean, maybe it's a little bit challenging because our office is quite crowded, but nevertheless, it gives you an idea.
So let's see how they perform. So we'll start with channel sounding outside and see how that goes. So just to explain a little bit of what we're looking at here, with channel sounding, it's quite a complex measurement process. I'm not going to go into all the details here. We have other resources that will explain that in more detail. But what you'll see is two sets of numbers in small font, the phase and RTT. The RTT stands for round trip time. So there are two basic measurements in channel sounding. There's a fairly coarse distance measurement by time of flight, essentially, and then one that looks at the phase differences between different channels. And then in the bold, in the green, you've got IFFT, which stands for inverse fast Fourier transform. Essentially, that takes all this channel information and tries to recreate the original pulses, essentially by looking at all the frequencies together, and it's better at trying to sort out reflections. So the IFFT is really the number we're going to focus on here, as the kind of best estimate of distance. And then what we're going to do is on the bottom you'll see the physical measured on the ground distance, and then we'll see how well the channel sounding performs. So if we start the measurement sequence, we start at 1 meter, and you see the distance measurement there bouncing around a bit, and then we increase it to 2 meter by physically moving the poles, and so on and so forth. That we're covering up a few distances, up to 7 meters, 7.5, I think. Yeah. So you can see we've changed the scale slightly so we can fit it in, and then we get the highest one is 7.5 meters. Now what we found was that it kind of broke down above this distance. I don't think that's a fundamental problem, but the algorithm, the basic algorithm, sort of needs all the channels. So if you start to lose channels, it kind of won't do a measurement. But there are ways to resolve that. I mean, we have to emphasize the channel sounding software is fairly new, so it's probably room for improvement with it. On the other hand, at the same time, you have to recognize one of the drawbacks of channel sounding is that it's quite complicated, and that's never great. So now we're going to do the same thing for ultra wideband. So here you just have a simple time of flight measurement. You have one type of measurement, so it's a lot simpler. So we just put up the distance here. So if we again show the same thing, what we see is the first thing you notice is a little bit of what I call zero offset. So it's measuring 10 centimeters short, but that's pretty consistent over the different distances, as we'll see. But otherwise what you see is the measurement is a lot more stable. The variation is much smaller. It's not jumping about nearly so much, and we'll quantify that a bit later on. And yeah, that's pretty good. You've seen that I say it's about 10 centimeters short of the real distance, but that's pretty consistent, so that could easily be corrected for. And that pretty much continues all the way up the distance range. It doesn't really drop off, so we're jumping up to 10 meters here, and then yep, up to 15, up to 20 meters, and you're seeing it's pretty accurately measuring with that, yeah, perhaps maybe 10, 15 centimeter offset, perhaps, up to 25 meters, and so forth. So, and yeah, all the way up to 30 and 35 meters, and yeah, that's pretty much where we stopped. So it's quite stable, and there's no issue with pushing it out to 35 meters. So now we'll look at the indoor data, starting again with the channel sounding. So indoors, on the face of it, intuitively you'd think it's a more challenging environment. So let's see how it performs. So we'll set it off. We'll see the same thing again. The big black bold number at the bottom is the measured distance on the ground with the tape measure, and then the IFFT is the one number we're focusing on for what channel sounding is giving you. And again, you can see it's bouncing around. It's perhaps not so easy to compare it directly with the outdoor, but we'll do something to make that a little bit clearer later on. Overall, it's actually performing not bad. It's definitely getting, you can see to a certain degree of accuracy the distance, yeah, we're gonna go up to the around 7 meter mark where we start to have some problems that, as I say, will probably be resolvable longer term, but with some more work on the software side. So that's the channel sounding. And then finally we'll have the UWB indoor, and so same thing again. We'll just see how it goes as we move the objects around. And again, we're seeing quite similar results on the face of it to the outdoor measurements. Pretty close, and reasonably stable measurements to what we're measuring on the ground with the tape measure. So it's working quite well there. So yeah, this is the UWB in action. So that's the individual scenarios, and then now what we'll do next is quantify these a little bit better. In order to show this graphically, the results we're getting, so you've got UWB and channel sounding alongside each other here. So on the top you've got the mean measurement at each distance, the average, and we're plotting distance as measured on the ground against the distance as measured by the measurement technology, and you can immediately see visually the UWB looks to the eye like a perfect straight line. The channel sounding is, I mean, it's not bad measurement. If you take this average, it wobbles around a bit where the perfect reading, but it's pretty reasonable. What you do notice though is for what we've called jitter, which is basically the extremes you see at each measurement point. So you're getting a lot more variation reading to reading, and so for the UWB it stays pretty constant at about 5 centimeters either way, whereas the channel sounding, I mean, it's got this big variation around 2 meters. Not quite sure why that occurs, but and then otherwise you're getting 10 plus or minus 10 to 15 centimeters for each point. So, and then we've got this thing where it, for reasons that we probably can correct in the long term, stops working above 7 meters, but one would expect it's probably going to keep getting worse as you get further away. And then if we look indoors, UWB doesn't really change very much. You still got a dead straight line there, and the jitter is a little bit worse, but not very much more worse. It's still around about 5 centimeters on the jitter. And just to be clear, the reason we stopped at 7 meters for the indoor measurement is just we didn't have the space to go any further. We have no reason to think the UWB wouldn't continue to work pretty well, even if you went up to 10, 15 meters away. But we don't have that big a straight line in our office. You're looking at the channel sounding, again, the average is still a fairly reasonable measurement, but the jitter goes up, so you're getting, jitter of plus or minus half a meter, even at relatively close distances. And yeah, who knows what that would do if you pushed up further away beyond the 7 meter mark. So it can be, the channel sounding is getting a bit erratic as you push on from there. So I think it's been interesting to put these technologies side by side and see how they compare. I don't think the overall results are that surprising. The UWB does show itself to be more stable, more precise, but the interesting thing is how close the Bluetooth channel sounding gets. Now, to be clear, this isn't because the UWB device is better than the channel sounding device. The UWB technology is pretty much designed to do this distance measurement, and the fundamental physics behind it means it really should do a better job. The counterpoint is distance measurement is pretty much all you can do with UWB. I mean, you can do other things with it, but the reason it was been built is to do the distance measurement function in one or more ways, and so it's a dedicated device to doing this. Obviously, the Bluetooth, you get a channel sounding is a new feature that's been added to all the other things you can do with Bluetooth, like general connectivity, streaming audio, and so on and so forth. So yeah, the two technologies have different pluses and minuses. Bluetooth channel sounding, it sort of comes for free with Bluetooth. Every phone's got Bluetooth. Lots of applications are going to need a Bluetooth device anyway, so you can add channel sounding to it without really adding any cost. You don't need any extra hardware. You can just put the software to do it in, and there you go. Whereas UWB, although it is appearing in quite a few of the higher end phones now, it does generally require additional components, so it's going to be a more expensive solution, but it does give you that advantage of precision. Now, as we saw, if you do some averaging on the channel sounding, you do get quite a reasonable result with it. However, one has to add that with the channel sounding, for each measurement, you're doing exchange on all of the Bluetooth channels. So you're doing lots and lots of exchanges. And then if you do averaging on top of that, of the different overall measurements, then each measurement is taking some time. And if you're talking about if you want to track, say, something moving, even at moderate speed, you're going to have quite a bit of delay. The UWB is very quick, and even taking a single point-to-point measurement, you get a good result. And it's done very, very fast because it's based on very sharp, well-defined pulses. So it's a very quick exchange. So in the end, you can't say one's better than the other. It depends what you want to do, and what degree of accuracy you need, how quickly you need your results. So there are many factors that go into this. As I say, at Insight SIP, we have solutions in both. We're not trying to push one technology over the other. So the aim of this video is basically just to see how good it gets, and try and go over some of the advantages and disadvantages. Obviously, if you want to know more, then you're obviously very welcome to talk to us about these technologies and what they can do for you. So I hope you found this interesting and informative. We have a lot more resources on our website that tell you more details about the technology, how it works, and why they perform as they do. Why UWB is gives you better measurements, and what the limitations of channel sounding are, because really channel sounding is a very clever technique to squeeze as much as you can out of Bluetooth, which was never designed to do this. So yeah, so we go into much more detail. So this is the ultra wideband. We've got our product page. We have white paper explaining more about the distance measurement technique, and a video that goes through just more in terms of the technical side of how this technology works. And then also for channel sounding the same, we've got the product page, so you can find out about the product that we're demonstrating in this video, more general information about all our Bluetooth modules, and a white paper about channel sounding, and also a video webinar that is really, again, talking about the product and the technology in more detail. So the aim of this one hasn't been really to delve deeply into that, but more just show you some side-by-side measurements of the two technology. So I hope you've enjoyed it, and thanks for listening.